Oh, maybe it's
There
not.
we go. We're live.
All right, welcome everybody. This is the Robotic Society of Southern California, our monthly meeting. We have three speakers today. We're gonna kick it off. Starting with Glenn. Yeah. All right.
We don't have anybody.
Okay.
We don't have anybody outside this.
All right, let me go ahead.
Yeah, we're not getting lost from Canada or. Sergey. Yeah, he's been connected. He's been joining occasionally. Alabama.
Is it Alabama? It's not Georgia? Same.
All right. All right. Good morning, everyone. As will probably hopefully be the case for the next several months, I'm going to share with you what's going on with my bot Alfie. Hardware-wise, I consider him hardware completed as of last month, so it took me about 2 months to figure out design, order, and assemble, which seems like a long time to me, but I think it was just long enough. Oh, yeah. We'll move this guy in. So he's hardware complete as of last month. I put him on the scale this morning. He weighs 22.5 pounds, a little bit of a hefty boy. Because of the placement, I put the battery as low and as centered as I could. But due to the weight distribution of the robot, he does lean backwards about 5 degrees. I was thinking about trying to move the base plate forward another centimeter, another 10 millimeters, which might help a little bit. But at that point, I don't think I'll have clearance for the cables that go from the head through the extrusion down. I don't think there's enough room, so we might just be a lean back bot. I've still haven't been able to communicate with the stepper driver. It's a serial UART. My next game plan for that is that I had bought a little USB to serial converter, and then I ran a USB cable down. My IndyDroid Nova supports 3.3 volt serial UART off of the GPIO pins. So my next game plan is to connect it directly to the board. At that point, knock on wood, hopefully I'll be able to talk to it. For controlling the drive wheels, I just have simple motor, rotational velocity, acceleration, and distance placeholders. I might move it over to the tele-op twist message at some point before I start really writing code for it. And the main reason, and we'll spend probably the last half talking about this, is safety. So I haven't wired up any of the ROS messages to command or move the base or the arms yet, because I don't feel like I've put enough thought into safety. And this doesn't mean like robots going wild, stabbing soldering iron. This is just, if something goes awry, will the robot continue driving until it hits a wall? Or, if you lose signal with the mothership, so to speak, what are the arms supposed to do? For the drivetrain, you may want to check to see how fast you're moving and then ramp down the speed because it's top heavy. And for the arms, maybe part of the game plan is to hold your current position. So I want to chat with you guys about that towards the last half. And so hopefully I'll have most of these things knocked out by the next meeting. Also, the concept of zero out and calibration of motor positions. Now, each servo motor has a 12 or a 14-bit encoder that gives you at least 0.3 degrees and maybe less than that accuracy in measurement. But when you're setting it up, nothing's ever aligned perfectly. So you can adjust what you consider to be the zero position, which I like to do. I like to find a zero position, then you're going plus negative degrees to move. And so how do you figure out how to set that between the real world and the software so that when you say hold your arm out at a 90-degree angle, that it's actually held out like that? Right? So I haven't quite figured out a game plan. And the truth is there's no right answer. The real world's messy, so you do as best you can and then deal with the results. There's also a small issue where so this is a MicroROS spot, and we're going to gloss over a lot of the MicroROS weirdness. But if the MicroROS board loses communication with what is called a Raspberry Pi, it needs to know that, and then it needs to reboot. So I need to write that so that as I'm updating code or something happens, and that I can still communicate with the daughter boards in that case. Also, all of the support services in the robot need to be brought up automatically. So the cameras, the microphone, the MicroROS serial transport nodes, I need to make those into a ROS2 launch service, and then write that into a Linux system bring up service that runs automatically when the robot boots up. It's if I search hard enough, I can find a couple of examples. So I'll be able to do that. And if all goes according to plan by next month, if I'm taking a slot next month, I should be able to demonstrate some capability of tele-op arms. So I'll make tele-op arms and I'll wire everything up, and then we should be able to experiment a little bit, and I'll tell you all about that next month. So I came up with a visual aid this time. I'm very excited about this. I drew up a quick function diagram. Can you make it small? Okay, no, okay, that's fine. I'm blocking out. There you go. So this up a little bit. All right, there we go. So this is Alfie's block diagram. Now the heart of Alfie is an Android Nova. It's a 16 gigabyte RAM, 64 gigabyte eMMC, Raspberry Pi shaped board, super beefy. It's got an NPU in it. And then that in turn connects with a bunch of peripherals. Anything in blue is USB. So I've got the USB directional mic and the USB depth camera. Because I fabricated my own cables, I don't get USB 3 speeds. So the O2 Lite will be limited to USB 2. Also, I don't know, Brian, if we've talked about it, but Jim and I have talked a little bit. It's super picky about the type of cable. And at least in my case, I haven't found a USB 3 cable that'll work on it yet. So
There's guidance on that. You need so many megabits cable USB 3, or it won't work.
okay.
Wait, which talking about?
Oh yeah, my OP light comms are under
yeah.
USB 2.
Oh, yeah, that
Yeah,
is, I had to ordered this a USB 3. Top of the on off Amazon, had to replace my existing. And I think I got rid of most of the problem. Even the cord to the Teensy, I had problems with. That's only USB 2. So from the Raspberry Pi to the Teensy, I was having upload problems and occasional. Well, that problem where I was on the Tuesday call and it was like intermittently not working, intermittently losing connectivity, or or when you're just driving the car, it would like stutter.
Oh yeah.
And I think there was if I replaced that cable too. You have to replace. You can't use cables lying around the house for your robots. Apparently, that's a big no-no. Like from cell phones that you bought or whatever.
Yeah. So yeah, I rolled my own USB 2 cable, which is the other reason it's limited. In terms of bandwidth, my startup launch file for it is going to bring up all the cameras at 5 frames per second. They top out around 8, but they fluctuate because they're all trying to saturate the USB bus. And then I'm limiting the compass and the accelerometer to 40 updates a second. And that only should be taking up about 75% of the available USB 2 bandwidth. And 5 frames per second is more than enough for my use. So that's kind of where I'm at on.
Yeah, I'm keeping all those pretty low, to start with all those.
Yeah. I do the opposite. On the OD, use the full big images. But I had tiny images coming out, like 320 by 160 or 160 by 100, very small images, but fast.
Oh, okay.
Because the rest of your system probably doesn't care about the images. Like you want it for debugging purposes, but all your processing, I'm guessing, is on your O2, right? You know, your image, your AI,
Right,
your
yeah.
CV and stuff is on your O2, right? So I prefer the faster frame rates.
Oh, okay. Yeah, and that's absolutely true. I think it's passing 1280 by 700 images, but yeah, if you tune down the resolution, then I could bump the frame rate to 15 or.
Yeah, so I think that's these tiny images, like they're ugly, but everything works great.
I've heard that with like classic machine vision, at least, yeah, smaller images are fine, and people always crank up the resolution too high.
Okay.
Well, don't forget the convolution networks, they step down the image. So if you already start with a 128 by 128, you're gonna end up with a 4 by 4 by the time the convolution network.
AI can be different.
So you gotta start with something reasonable for the
So-
convolution network to work.
In your OD, you keep the images big. I think it's 600 by 600 for our.
640, yeah.
No, it's a weird number, like 600 by 600. It's a weird number.
Oh, you mean for the input to the model,
For the neural net, right?
or you
But
can
that's-
lower?
But that's all inside of the OD.
That's inside the OS.
Once you go to the ROS and your communications, and all these serial ports and stuff,
Then you don't need it.
right? Then you don't need, then you just have a small image flying around. Okay.
Yeah, what do you even do with those small images? Are you for display or just for debugging?
All right, yeah.
Ellen, isn't the requirements based on how fast the speed is? I mean, what's your maximum speed? I mean, you probably don't need a lot of frames per second if you're not moving fast, right?
Well, there's, the camera is capable of 30 FPS. And at varying resolutions, it can cert at least, maybe even 60. I haven't even checked that yet.
A good light, you know?
And then based on USB 2 and the size, you have to squeeze it through the USB pipe, right, to get it to the other side. I don't expect to be deep processing images more than 1 a second, but I haven't done anything interesting yet. So these are the guys that would
But I
know.
mean, there's a big difference between that robot and like a car that's going at 15, 20 miles an hour.
Oh, I see. Okay, maybe a minimum FPS based on how fast you're going.
Yeah,
Guys, do you have an opinion on that?
I don't think it's gonna be going real fast. on
No, no,
Yeah.
it's no.
But so when you're doing your gripper, so if you're looking at the gripper and trying to grab something, you know, here, you don't want 1 second, that's really slow.
Okay,
Right.
yeah.
Another consideration is some people like to, and I think I would like to do it, is videotape the progress of my live as the robot does its thing, record the video from the camera at high resolution, or at least at 640, whatever, some resolution. That's
Yeah.
And Nathan Lewis, the winner, who's going to speak next month with us, the winner of the Robomagellan 24, he does that on his. I'm not sure how he does it, but he's record. I mean, you have to go. Obviously, you can't. These cameras don't have you can't plug in a memory card into the OD. It has to be through the USB, recorded on the Raspberry, recorded on the computer.
Yeah, well, and then since we're all doing raw spots, ROS bag would be I think would be a good option for that. You get your metrics, your telnet, like you get all of it captured, and you can replay, especially if you're troubleshooting.
So then
I haven't done it yet, but it sounds.
I haven't
like
either, but then you'd want, you want a little bit, you want something, reasonable resolution
Yeah.
for viewing later. So I don't know how you do that and fit in the,
I don't know, ROS tags already get huge, and with big images, they're gonna get.
Oh,
maybe not
compressed
ROS.
by frame.
Yeah, can you imagine?
Well, the OD already has a streaming capability through the software. You can record the samples code for it. And it does it efficiently, pretty efficiently, I think. With HEVC or encoding and stuff like that.
So yeah, the last two USB cables are USB to serial to those wave share general board driver boards. Because they're ESP32, the maximum comms rate that they can support is either 1 megabit or 992 kilobit. Moving through each one, the top one controls the lights, the bottom one controls the base motors with encoders. And then I split the left arm, right arm, and head across the two. Because I'm bandwidth limited, I had to put some thought into how to get messages back and forth from the servos, as well as how to communicate out in a way, because my target comms rate is 100 hertz. I want the system to be able to support 100 hertz status updates and 100 hertz command updates. And so far I'm doing okay. The ESP32 boards are dual core 240 megahertz. So super beefy compared to an Arduino. I would say on par with the Teensy 4.1, but I don't know if either one supports hardware floating point. But ballpark, they're a lot of fun. So my Core 0 focuses on communication with the serial peripherals and updating status from the peripherals into a data structure. And then my Core 1 handles all the ROS comms, sending out status updates and intake of commands and distributing it out. The stepper driver was USB over serial, and I could never get it to work. So I've subtly changed the coloring of it. And it was my digging into the robot and kicking out the USB hub that resulted in this.
When did that happen?
You know, I'm not sure. Luckily, the buck down converters are sold in a 3-pack for $20.
Oh, that's
And the first one, I knew how I blew it. There was a loose piece of metal rolling around, and no excuses, but I think it's funny, so I had to share it. This one, the pool says that it's a hardware short in the supply rails. But yeah, when I put everything back together after touching it, because why wouldn't you make major changes to a robot a day before you were talking about it? Let out all the magic smoke. There was a pop and a smell of burning plastic. And so I popped in my third and double checked for little pieces of stray metal or whatever. Couldn't find anything. And when I powered them up, I get a positive light on the power switches, but the power rails aren't energizing. So
This is which one is that? That was a power converter.
that's
there?
a buck down converter.
Buck
Yeah,
down.
it takes it from 38 or 36 to
So your battery is
36 volts. Some yeah,
so like is it
LiPo.
like
Yeah,
so
yeah, it's a
pretty
good
high
battery.
voltage.
Yeah.
Did you pull the heat sink off? That's whatever they're using.
Oh, I should have just brought it to get some more experienced eyes on it. I didn't. That was the only magic smoke that I saw when I looked at it though.
I want to see if the cuts are damaged.
Yeah.
So,
I have a question. You use the ESP32s with MicroROS, right?
Mhm.
And you said you have to have a washdog to reboot it. I wonder, like,
So yeah, so the mechanics of it is that when you bring up the ESP32, I have like a 7-second wait. It opens up the serial connection. It waits 7 seconds, and it assumes you have a connection and establishes all of its services and topics, and then you're good to go. If I stop the MicroROS serial node and then I restart it, the ESP32, because my code's 101 code, it doesn't even look for that, so it gets stuck and you lose comms with it. So
I might have a fix for you.
oh, that'd be great. Yeah, so when I mentioned it during the ROS meeting, Jim actually pointed out the Linabot 2 source code tree, which has one way of dealing with it. And then Mike Wendy shared a document and a GitHub to the way he handles it. And so I think the general gist is, because I have to do a periodic time sync. So as part of the time sync, I can take a timestamp. And so if after X number of milliseconds, I don't see that the time's been updated because of a communication failure, I can roll it up into a watchdog and then just repeat.
Yeah, and I think the reason why, at least on mine, the reason why I got dunked up when the controller went away, is trying to send messages because of quality of service. It's trying to resend them over and over, and it's like totally bottling it up. So my experience, I just changed the quality of service to all of my sources.
Yeah.
And it all cleared up, and I can turn on and off that real.
Really? So you can turn off MicroROS serial and turn it back on and your Teensy or ESP continues to communicate?
Yeah.
I will look into that.
Oh, you mean
Okay.
the agent, you can turn off the
The
agent
agent,
and
yeah,
it's,
the MicroROS serial agent. Blah, blah, blah.
why would you, or,
I
yeah,
do
why
it
would you do that, or?
Because
Well,
I'm restarting things
or
all the time, like how it restarts, but I want my low level control to always run. That shouldn't stop just because the pipes not there. Or in your case, or whatever you're.
In other words, yeah, like when I launched this like bring up that launches the MicroROS plus the agent plus some other things. But I could just launch the MicroROS alone. Well, the minimum I think I do is MicroROS agent and the Teensy. Well, the Teensy code's always running.
Yeah, that's the thing.
Is that what you're talking about?
Yeah, yeah, when the TC always
The
runs.
Teensy code is
And
always.
regardless of whether the agent comes or goes, you want your.
Yeah, so
Ideally, yeah.
Yeah, that's what I went up against, and maybe we could talk later.
Yeah, no, I'd
Yeah.
love to pick
Yeah,
your brains on it.
Yeah,
For me,
same
it's quality
thing.
of Service.
Same thing, my Teensy code is running all the time, it never does, it rarely requires a hard reboot. Because it detects agent connected, agent disconnected,
Okay.
and well, this the Lino too, I mean, I'm not a.
Yeah, so I'm
not
gonna read
the
through
guy who
both
wrote
those,
that.
see their approach, and yeah, Brian, we can talk, I'd love to pick your brain about what worked for you.
But yeah, you're saying what happens, you with a less sophisticated approach, it requires rebooting the Teensy alive, essentially.
Yeah, because as of right now, if I stop the agent and I restart it, comms with the ESP32 aren't recreated, and so I have to effect a reboot of the ESP32. With the way things are right now, but yeah, I'd love to pick your brain
You
on.
mean that, yeah, there's a right, that whole agent connected, agent disconnected state machines seems to be one way to do it
Yeah.
anyway.
Just to remind you of the nightmare I created for myself, here's the electronics bay at the bottom of the robot. I've got a couple of fans pulling air from the front and pushing it back. So everything's actively cooled, and as long as I don't let the magic smoke out, everything works. It's been running constantly since our last meeting. I just let it run in the background. My e-bike battery is such that it'll provide power even when it's being charged. So I just have it sit in my office, plugged into the charger and powered up, and we're good to go. And just to embarrass Alfie a little bit, here's what it looks like when I'm working on. I'm working on him. He does a handstand. I precariously balance him and move his arms around, and that gives me access to the electronics bay.
Nice.
So he spent a lot of time upside down yesterday. Poor little guy.
Head rush.
Yeah.
You balance everything on the very top.
Yeah.
Take it out.
Just like, for most robots, you gotta build a stand and test it on it. In this case, you have to build an inversion.
Yeah.
A couple.
About that, sure.
So I thought I had, it was on, sorry, I had a computer problem this morning. I had a screenshot of him up in, Foxglove, which is, in my opinion, the next generation of RViz for robot visualization. This will be a little hand wavy because my screenshot is on the other computer. There was an interesting thread about managing robots over at HP Robotics where someone asked if you could input commands through RViz or Foxglove. I've never done that, but apparently there's ways of doing teleop where you can populate sliders and whatnot. It's pretty cool. All right. So the again, just in case anyone is looking for something super small, and the line between full-blown x86 or x64 mini PCs and single board computers is getting blurred more and more every day. This is what I would consider to be among the best of the best right now for an ARM-based one, and they are more expensive than the Raspberry Pi, but they've got all kinds of fun doodads on them that you can make use of, including GPIO, which I'm already taking advantage of. The general driver boards were bundled with the ARMs and with the base. So they support serial comms with the serial servos, motors with them. Okay, stop with it. motors with encoders, or just plain motors, Wi-Fi, Bluetooth. It has built-in current sensing as well as a 9-axis accelerometer IMU. Unfortunately, due to space constraints, I don't have access to the compass portion of the IMU or the current sensing. And that's because in order to get everything to fit in the electronics bay, I had to do something awful. I carved off the second 40-pin connector. And so I'm not sure why that would have an effect on the I2C comms or power for some chips on the other side of the board. But it did. So I don't have IMU or volt, and that's not that big of a deal. It was a nice to have anyways. On the upside, everything fits inside the electronics bay. So I'll consider that a network.
I'm not sure you can cut that. That's
Oh, Dremel.
Yeah. Do you see nothing on I2C or it just doesn't work?
So because when you run the code that communicates with one, it's just the boilerplate code that they have from the manufacturer. I time out.
Yeah, I see that they might have the pull-ups on the part you cut off.
Yes.
And you can put your own pull-ups in there.
It's interesting you mentioned that because this connector right here is actually for an OLED display, which is also I2C. And I lost connectivity to it, but what I ended up doing is soldering the SCL and SDA lines from there over to where they appeared in the first 40-pin connector, and I got it back. But only for that one. I don't have. So I think I'm just going to cut my losses. There's no room for me to put in a full one, and I don't really need it. But it was a little sad because I'm like, because these are all straight through. This is a pass through from one 40-pin to another. But I thought, yeah, but apparently something routes all the way over and then back.
Something's embedded in one of the layers.
Yeah.
4-layer board.
Yeah. So a little, but everything else works.
So these boards are from the manufacturer to run the servos. They have some code, whatever that's preloaded, that you're adding to it or modifying it to add the MicroROS, or do they provide that?
Yeah, they didn't have anything MicroROS. So after I got the hello world of MicroROS running, I started copying over the files.
Okay.
Well, first I would just run the code as is and push it to ESP32 to see that it worked, and some of them didn't. And then as I start creating the topics and the messages and the services, I start copying them into my Alfie directory.
But this board has like, so all the GPI outputs are connected to all these features.
Yeah, 100% connected up to everything.
So where's all that configuration done? Is that partly in their code, or are you replicating that, or how's that? How do you put it all together? Because their code has, all the code to do the IOs.
Oh yeah, all of the peripherals are fixed I2C address, so there's no configuration in the sample code that was provided.
Okay.
It's just how to communicate with the IMU or the voltage or the current sensing and stuff. So the IMU stuff I'll take out, the current sensing stuff I'll take out, and then the serial drivers to communicate, because every serial servo is a little bit different, even though a lot of them look the same. So instead of, they had a standard serial servo library that I could have just imported, but I'm like, I don't know if all the memory locations are the same. So I just copied in and then filled in the blank of their defines for their memory map. So it matched their documentation. But yeah, so far so good.
It's not like that. Yeah, this is not Arduino compatible. It's sort of like it's in the BIOS of the system connects directly to that to those.
Yeah,
memory mapped IO.
all of the peripherals are hard coded to respond on certain memory addresses and lines, and every line's used. I couldn't even, there's no extra lines that I could use for UART for troubleshooting. Like everything's in use on the ESP32, but I just blink the lights now for diagnostic on troubleshooting. So in the spirit of systems integration, now I am going to skip over all of the detail of getting MicroROS running and stuff. It is arduous. It's a dark magic. If you have a pre-existing code base to work from, that's awesome. But using ROS to communicate with all the peripherals because these two need to communicate with the main board. And then for some higher level stuff, I'm leaving open the possibility of my desktop workstation being the brain of it, right? All these together, could I roll my own messaging protocol or use MPX? Of course I could if I wanted to, but because I'm using ROS, I can use their mechanism for message definitions and message type and message passing and quality of service. Are they fire and forget? Do I need to make sure they're received? So in order to get the boards to communicate with the main board and future workstation, we're going to use ROS. So I need to define some message formats to be able to communicate back and forth, not only commands, but state. So a lot of this is based on reading through the Unitree go-to ROS implementation. It's a quadruped robot. It's not a lot of similarity, but in terms of whole state robot control, that's what I modeled it after. So moving up from the bottom, there's a serial servo command, and this is the command that's used to take control of a single servo. And the first one is true or false. If it's set to true, it'll hold steady state. If it's set to false, the servo relaxes. We will communicate position. So my robot, my rules. ROS wants you to communicate in radians, which is more convenient when you're doing trig calculations. My mind's never worked in radians, so my robot's going to accept commands in degrees. It's the same thing as Omniverse, so I feel like I'm not too out in the fringes with it. And the way that I like to arrange all of my servos is that their neutral position is 0. So if you're an arm, if the arm's hanging down, that's 0. If your elbow moves forward, that's plus 90. And then if you're a robot, you move it backwards, that's negative. That's the way that I like to orient the position and the feedback control on my servos. Also, you can specify the speed and acceleration that you want to get to that position. So you have a lot of control over how you get from point A to point B. And just recently, when I recompiled my MicroROS messages, I realized that it would be handy to include a torque value. The torque or the load that you get from the serial servo isn't exact. It's very ballpark. And for most of the arms and stuff, you just want to have maximum torque. There's a built-in watchdog in each servo that manages the load and the temperature. And if you overload a servo on its own, it will report an overload condition and disable itself. So that form of safety you get built in. Now, ideally, if you want to be smart about it, you want to monitor that and take some action before the servo overloads and turns itself off and relaxes, but you get that for free. Yeah.
On that. So if you're holding the arm out, maybe even with something in the gripper, and there's a heavy load on the motor, you just leave it there. It might get to the point where it overloads,
Correct.
and then it might just drop.
Correct. Yeah.
So are those, are the motors that you're using for like the shoulder joint, they're powerful enough to hold it out there for a period of time?
Your observation is 100% correct. In its default configuration, they claimed it could hold a load of 500 grams fully stretched out. My final arm is about 4 inches longer. And it's not designed to hold maximum torque all day because there's no cooling fans or anything else. So as part of safety in my control regime, I need to monitor that and take that into account.
It looks like a human arm. If you get tired, you're gonna lower it.
Just like a person, yeah.
Yeah.
If you do planks or hold it out, there's only so much time before you want to relax.
Yeah.
And ideally, you want to maintain some control over that. If you're waiting until the motor shuts itself off, then maybe bad things happen.
Okay.
Relatively bad, right?
If you had something in there, you could put it down before it gets too.
Right. So yeah, as part of safety, you want to monitor for these potential overload conditions. Like we're talking super high level at this point. I don't have an answer for it, but if you're in danger of overloading, you need to adjust your strategy. Maybe it's setting something down. Maybe it's right? But yeah, once you're monitoring it, you have far more control over possible actions than just relaxing.
So there's feedback from the motors that tell you what the load is, what the torque is.
Yeah, it's indirect and it's not precise, but yeah, it's definitely present. And the whole reason I wanted torque was because I wanted that level of control for the grippers. I thought it would be handy to be able to specify irrespective of, like, let's say closed is 0 and then open is 45, to specify then a negative, and then specify a maximum torque that it would honor, just so that you don't burn it out. So the other half of that, and so this is the basics of a command message to do a servo. And none of this is wired up yet because of safety, which I'm excited to chat out with you in the latter half. So the flip side of that is a servo state message. And you'll notice the first 5 parameters are the same as the command. So 100 times a second, I'm going to respond back with what I believe, what I know that the last command was for it. There's also a status flag I'll move back, and then the rest of them come from the firmware. Is the servo currently moving? What is its current position, speed, and load, voltage, temperature, and current? So I'm getting all these back 100 times a second. And so the opportunity exists for some really elaborate oversight, high-level watchdog type thing, to monitor for. You've asked me to hold this 500-gram load up at arm's length for a minute now. Maybe not. I also have an IMU state. This is based on the sample code. It's not the built-in ROS messages didn't really quite fit for me. So this is what it passes back. And finally, as of right now, for the motors and the base, I just sketched out an enabled velocity, distance velocity acceleration for a command. And then for the motor state back, I'll respond back with what I believe the current commands are, as well as whatever the current distance velocity and acceleration is, again at 100 times a second. So these are the base messages, and all of these come together in a controller state message. And here's what I pass 100 times a second. The IMU state. I have 10 slots for servos, and so those will be populated based on whether it's left or right. The left ESP32 has all 7 motors for the arms, and then the 3 motors for the head. And the right does not. So there's 10 instances of serial servo state. And then there's 2 instances of motor state. And again, this might be replaced with a twist or something more advanced. I'll look over the Linobot and Mike Quimby's code to see if I want to change my control strategy for those. And just looking at how it's done on the Unitree Go2 robot, they have a controller command message where they just bundle everything up into one. So I decided to do that the same way. And again, none of the commands are wired up yet, because I want to talk to you guys about safety, and I want at least some element of safety in before I start controlling the robot. Now, in addition to all that, each of the servo motors has a configuration. They have a memory table. And during setup and configuration, you need to be able to update their configuration. So in order to do that, I created 2 services. And each one of my control boards listens to read register and write register topic. And to read a register out, you specify the servo, the reg size, which is either 1 for 1 byte or 2 for a 16-bit word, and then the address of the register, and I'll respond back with a success and the value. So if I ask a status or a value from a servo that's not there, there's a communication issue or it's an invalid, success will be false. And then if I know the response back from the servo, true, and then the value. The other half of that is write register, the same first 3, which servo, 1 or 2 for reg size, which register, and you'll pass the value, and then the response will be success, true, or false. And it'll do that. So all these things, the services we're running right now, they'd be running right now if I could power up the robot. And I know it's killing me because last month it was on and now it's not. So I'll get that figured out. So, in the ROS way, you define a series of messages. If you can find an existing ROS message format, and there is a large library of pre-existing messages, made by people way smarter than me. But because this is a unique robot, and I couldn't find anything that exactly fit. This is how I chose to implement controls and status for the bot. Yeah.
So the read and write registers, so those were separate type of parameters than you're sending in the command, right? But
Correct. Yeah. Yeah. These are out of band services that will read and write values from the memory map of each individual servo. Right. So when we're getting into the calibration stage, I'll get the servo into a position where I want this position to be the 0 position, right? Or the, yeah. So once I get that, I'll send a write register command that tells the servo what offset to honor so that this becomes the new 0. Yeah, things like that.
nice.
Things like that. So. So yeah, my hope is over the next month, after our discussion, I will have worked out enough of safety to wire up all the command types. And then construct a quick tell-off pattern because I have all the components. And then we should be able to at least do tell-off next month and do some fun stuff. But what I wanted to really bounce off of you was, and do a deep dive, is the concept of safety. So, oh shoot, I don't know if I have it. Let me see if I can find it real quick. It's a funny video. I linked it into Jim's message, Jim's post for last month to just drive home the point. So, a second to find it. Okay, so this is May, April, where are you? Processing request. Right, so this is a racing robot. There was a mishap. And so during Robomagellan or Robo games where they talked about having safety and dead man switch, this is the exact reason why, right? Especially if it's a high speed or a dangerous robot, you want to make sure that you have a non-ambiguous way of cutting power and bringing the robot to a stop quickly.
Guy's standing on a racetrack.
I know, right? Like he's asking for it. I love that.
That's user error, human error.
Yeah.
Did he actually fall?
You know, there
more
can't
safely than
be
robots.
proof anything, so the universe just comes up with a better.
Oh, yeah, preach, brother. I know. And this being my first mobile platform, the fact that it's motorized and could drive around, I mean, albeit not fast, I wanted to brainstorm with you guys for a minute about strategies and the things that we can guess will happen and the things that I didn't think about. And just starting with the base motors, like if this were an RC car or a contest, you would have like a relay and a radio switch of some sort, and that when you're holding on to the switch, the relay is energized, and then the switch is really energized, right? Like that's more or less, no? Okay.
We should, maybe.
So on this guy, there's several levels of mishap something's wrong. And as an added bonus, my robot's top heavy. So if I were to cut power in the middle of forward motion, the robot would fall over, which is not ideal. Right? So to just think through, without even defining what would result in this, we know that a watchdog or a high level control that says, okay, it's time to shut the robot down, it can't include just cutting the power. So it has to include reading the encoder history, looking at the current velocity of the wheels, and then gracefully ramping that down before reboot, right? So that seems pretty straightforward, but that's the easy part. The hard part is, what are all the different conditions under which you would want to do we'll just call it a shutdown, right?
You're talking about automated, not.
Yeah, yeah.
Not human loop involved in the loop.
Yeah, and the thoughts crossed my mind to like have,
Yeah, I mean, yeah, that's a really good fail safe.
yeah.
Then the human can look and see it's getting into trouble.
Yeah, well, that's not good. Yeah.
Yeah, automating that is a whole other.
You have unused pins on your processor board.
On the Integroid Nova, I have a lot,
I was gonna-
almost a lot.
I was gonna say, there's a whole thing about shutting down Linux on Raspberry Pi, so that they run some kind of a daemon and hit a button and gracefully power down.
Yep.
I would take a hard look at that and see how they do that, see how that would integrate, slowing your motors down.
Right. And when you're looking at it, I've got brainstem level smarts, and then I've got the Nova, right? So in the case where I lose communication with the Nova, so this would be a brainstem level watchdog, right? At that point, what do I want to do? So I have a watchdog that periodically checks something to make sure I have comms. If I don't have comms, and I'm doing 100 hertz updates, so let's say 100 milliseconds, right? So, or maybe even 500 milliseconds, half a second. I lose comms with the main board. This means that something's gone wrong. So I no longer want to honor the move forward at 5 meters a second, or, sorry, 5 meters a minute. It's slow, right? So one level of it at the brainstem level might be if I lose comms with the Integroid to measure my current velocity and then to ramp down and reboot, right? And that would be one way at the brainstem level to ensure that if something goes wrong between these two guys, that I gracefully handle it without stopping suddenly and falling over. Wouldn't be the end of the world, but prefer not to.
Yeah, I would recommend that Mike Wimble, Homebrew Robotics genius, he's got the new meeting on, he's forming a new.
Another ROS6.
Yeah, another, maybe if you prefer like more in-depth discussion versus the circus of
ROS2 now, that's 100% ROS2.
or I mean, the circus of like the normal homebrew robotics general meeting, that's more of a social event, but this one is a deep dive into different people's robots. But Mike Wimble is a very big proponent of safety. He's been doing it for 20, 30 years. I don't know how long he's been doing robotics, but he's done it so long that he's come into all problems. Wires popping out, things frying, everything's happened to him. So he puts in safety at like every level. So, and he's documenting it. So I'm definitely, and he's publishing the documents. So I'm really.
So most of his code is probably error handling.
Yeah, it's and it's hardware too. He's got amazing, quality of connectors and all sorts of things going on. It's like many levels, but he takes safety extremely seriously.
Yeah,
Which most of us kind of go, I don't have time for all that. But when you're doing a robot like yours, you have no choice anymore.
Yeah. Yeah, and so I took a quick glance at the Linobot 2 firmware. It's competent, right? But I didn't read through it a lot. When I just took a glance at Wimbley's code for the Teensy, like I'm in intermediate-ish level, like I can figure out my way around C++ source code. I'm obviously not a developer, but when I looked at his source code, I'm like, oh, this is something you can learn from. Like it's obvious looking at it that the guy knows this. Yeah.
I haven't even looked.
Yeah. So I'm looking forward to spending some time to integrate some of his approaches in that. But yeah, so for the base motors, I think we're okay. In the short term, all my smarts are here. So if I lose comms, I can shut them down. Perhaps I also want to look for a higher level heartbeat. So in the ROS stack on the Android Nova, when you run the full stack that's doing something, perhaps it sends its own heartbeat, but I can also keep an eye out for it. Because losing connection with the Android is certainly one failure mode. We want to handle that. But then if the higher level code, maybe it monitors for a higher level heartbeat as well. And that if the higher level code is no longer doing what it's supposed to, also do a graceful shutdown. It makes sense. I think I can roll that out.
So you can talk about losing, it sounds like it's a general, my experience is like this sort of slows down. And so instead of looking for the heartbeat or like when I connected to ROS, so you're responding to command cell or your own velocity. Well, that's got to be handled 10 times a second, and if it doesn't, it's shut down. So there's a whole bunch of actors on the way.
Yeah.
If they're not updating correctly, you can just stop. So
Yeah, just gracefully.
But yeah, not like you might be getting other things, right? The magnetometer might be coming in, but command bell's not coming in. So that's when they like do a little more granular.
Right, yeah, yeah. No, that's, I'm excited. This is my first mobile robot, so I'm a little bit nervous.
And when I look at this thing, you talk about safety, I'd be way more worried about things like tipping.
Yeah.
Yeah, so like, yeah, he says command to go forward and it's going forward, and now it's going up a little stair and it's tumbling. So you probably want things that they're looking at your accelerometer, looking at your RPY and all that stuff. If it starts going, like, you pick up something heavy, your motor's not gonna burn out, it's gonna fall over. Probably. Yeah.
Maybe, yeah,
Maybe.
yeah.
Well, and you're moving, like, there's all sorts of dynamic things.
Yeah,
You can look at the IMU and see what if something's going a little haywire in the accelerometer, then.
right, which gets back to the higher level stuff. So the OD light, the first one that I bought didn't include an IMU. In the documentation, it said that it did, but mine did not. So I was going through their forums and apparently they shipped some without for some reason. So I opened up a ticket and they cross-shipped me a new one. Awesome customer service, right? I would have preferred to have it the first time, but they didn't even make me ship it back because I was like, I don't want my robot not to have a face. So they shipped it out immediately. They gave me a shipping label, sent it back, we're good to go. The IMU doesn't have a magnetometer on it, it doesn't have compass. And so I'm like, oh man. So without the compass, I do want to monitor that because it's up high, down low. I'll be able to see pretty quickly if something that I'm doing is in danger of tipping over. And again, I'm going a little scattershot at this point, but I really wanted the compass in that IMU because I had this bright idea that I could train a small neural net to know what room it's in by doing a 360 and training the different rooms on it. And then once I do that, it's a simple matter of saying room B is east of room A. But without the compass, I probably
They don't come with a compass.
yeah, the expensive ones do.
Sorry, not the light,
Not the light.
It'd be nice to be able to somehow monitor the attitude.
Yeah.
But they probably don't have a way of doing that.
Well, I can infer it.
With acceleration,
with
whatever,
the
but,
yeah,
but you might be on, a non-even surface. That might be one reason why.
oh yeah.
So it'd be nice to have a way of actually monitoring the attitude. I don't know how.
Yeah, right, you have got
Hey, Alan, does this work?
Hey, that's perfect, Ross. Yeah.
It's Ross, yeah. I ran into exactly the same thing. I'm working on something that has the OD, except I bought it without it. Anyway, I've picked up a MPU 9250 and found a ROS2 driver that publishes the right stuff. I haven't got it working in the robot, but I'm counting on it giving me that, and it does have it has a gyro and a compass.
Yeah, and that might be an option for me. The only reason I can't do it immediately is I have all the cabling running through the extreme. And I can't think of, if I really had to, I might be able to figure out a way to get an extra set of lines down. But yeah, it might be using a discrete IMU in the head. If I can't get the IMU and the OP light to do what I need to. Yeah.
Were you able I've just hit the website from Amira, whatever the vendor for the Nova device you were talking about is. It says it's currently pre-order. Is that just a temporary thing, or were you able to get yours, pretty good?
Yeah, so,
Sorry, I didn't mean to divert you from your.
it's a really cool device. I'm happy to talk about it. They can be purchased through Ameridroid.
Yes, was on that site, correct, for 100 and they've got a deal on the high power one for $169.
Oh, wow.
Yeah. But it says pre-order only. Is that just they are shipping this thing, right? Or at least the manufacturer is shipping.
Yeah, I'm seeing add to cart on it right now.
Oh, okay.
But yeah, the my first one I did buy for the move that was pre-order, but yeah, they've been around for a couple of years now.
Good. And you can load no problem with loading Ubuntu 22.04 AM. It's an AMD 64, right?
This is an
Or is that on ARM?
drop chip ARM. Yeah.
Okay, so it's like a Raspberry. Okay.
Yeah, like a BP Raspberry Pi. But yeah, it's very well supported. They have a bunch of images available for it. And both times I've had a question, and I can't remember if it's a Discord or something else.
Yeah.
The Ameridroid guys are very responsive. So I've had nothing but great luck with it, and it's been nice. It is a little bit more expensive than the Raspberry Pis, but you do get a lot more with it as well.
What about is the footprint similar or is
It's the exact same footprint.
Okay.
Yeah.
COS?
So I could,
Yeah, Android, Ubuntu,
What are you running?
Debian. Because of the ROS stack, I'm running Ubuntu 22.04.
Right.
Yeah.
And so that's why you're able to use those WaveShare interface assemblies for your motors, right?
Yeah, exactly. And again, I'm going to be hand wavy for a minute because my robot's not powered up. But even developing for the Alfie as a platform, I don't need to connect directly to it with a keyboard, mouse, and monitor. It's set up as an access point. My desktop has Wi-Fi on it, so I connect back over. And then there are tools in Visual Studio Code that allow you to SSH over and operate on the device remotely. So I'm running Visual Studio Code on my desktop. It's connecting back over to the robot using SSH.
Yeah, I just figured out how to do that. It's the second greatest thing since sliced bed to VS Code itself. The fact that it has that, and then of course you can push and pull from your GitHub.
Yeah.
Anyway, sorry, back to you. I didn't mean to interrupt.
And then I even do my ESP32 platform IO MicroROS compilation installation. It's being done from the Unitree. I'm just triggering it all from here. Yeah, it's super sweet. We're running a little short on time, so the last thing I wanted to bounce off of you all while we're together is talking. So for the head servos, the head's not going anywhere. You could cut power to them. Who cares? In terms of safety, the arm servos are a little bit different. We already talked about overcurrent conditions or over temperature conditions, that if everything went according to plan, you would be monitoring this and come up with a graceful shutdown or lessen the load when it happens. But in the naive case, even where the ESP32 loses connection with the Unitree, the easy way would just be to disable the servos and let them go limp, right? And that's absolutely safe for the servos, but sometimes arms are carrying things. So what I was thinking was perhaps if we have a loss of signal condition and we're going into graceful shutdown, to just find whatever the current position is of the servos and then send that as a final and then kind of lock them in position. That's all I can think of really for right now to do it. But yeah, the manipulators make things a little bit more interesting because if you're in the middle of manipulating something, you probably don't want to drop it. Or maybe I'm just overthinking it. I don't know. But yeah, I'm kind of like, I'm at the point right now where I want to wrap up all of this boilerplate stuff and I want to do something with it. So, I'll work through like the watchdog safety code for loss of signal just to get the party started. And then, tele-op, I'll build the remote operated arm welder thingies. And then if all goes according to plan, next month we can play with it. We can do a little, can you grab the block or something. And that brings us one step closer to leveraging all the recent developments on deep learning control of humanoid robots. All for just a smidgen over $2 grand. Yeah.
Better than 30,000, right?
Yeah, for sure. So, all right, so that's all I got for this month. Hopefully I'll have more updates for you
I
next
have a
month.
question.
Thank you.
Thank you.
Something else is a little ignorant on this particular. What was your starting point? I mean, did you get the frame and the arms and everything comes together and then you just have to add the brains? Or what was the starting point?
Yeah, so
It's a kit, right?
well, the funny thing about it is 90% of it is off the shelf components. The arms are kits from WaveShare. I fabricated and designed the wrist and the hands. This is 1/3 of a Delta printer arm.
Okay, so you made this frame.
Yep, the base is a WaveShare kit. The OP light camera, the re-speaker mic array. This head is actually the top piece to the motorized base. So yeah, everything is off the shelf except for a couple of 3D printed parts.
Yeah.
Which I think is wild. This is the future we live in.
And it was based on, the inspiration was the Aloha Mobile, right?
Correct,
I don't
yeah.
know if you were familiar with that. That Aloha Mobile was the $30,000 lab robot of a similar.
Yeah, these guys
And
are
they
the
trained it
inspiration.
with reinforcement learning, which Alan is, I mean, the whole effort, you want to pursue that, I assume, right? The whole reinforcement learning
Yeah,
and make it do something like this someday.
yeah, I'm
Maybe
very
sooner
excited.
than, well,
Yeah.
as soon as possible.
Yeah, my first goal, which is a stretch goal, because I don't know if it'll get that far, is I want it to be able to high five. I want to get high five from it.
Oh, you're going for human,
too.
you're going for human interaction right off the bat.
I figured that would be fun.
That'll require the same.
Don't you want to cook one shrimp at a time? I think
Cook one shit.
Well, it's funny you mentioned that because I had to make a decision about halfway through assembly. The initial build of this guy, and during the break, I can show you the fusion files for it. Is the arms were flipped upside down into a mantis configuration. And in the mantis configuration, with this shoulder height, they could just barely see over and reach things on a countertop. I know I'm really teaching up here, but the guy's, it's like 6-year-old, so more down there, which would have been worked and it would have been far more functional. But I like the way it looked this way better. So I've kind of sacrificed being useful. Yeah, just like a 6-year-old. Yeah.
I'm gonna have to put away chairs first.
Right.
Immediately.
It might have been nice to have a bigger wheelbase. You got,
Yes.
it seems like for something that high, you really should have something, a bigger wheelbase.
Yeah, it's not because the battery makes up so much of the weight. It slide it.
Oh,
So with the battery, it leans back about 5 degrees, but it as long as I approach acceleration and deceleration sanely, the center of mass is really low.
We could even add training wheels for
That's what I was
testing.
saying.
Yeah.
You could, you know,
Yeah, I know I'm talking all tough, but like once the rubber meets the road, it's actually mobile.
When you start, you kind of having just played with the base for a while, I didn't have just played with the arms for a while, because all this, while it's taking its first steps, is dangerous. Like, I mean, you're just gonna lose money, right? That's all it is.
Yeah, no, you're not wrong. You're not wrong.
yes.
But he's so cute.
It's adorable, but like, when it started, I just do the base all by itself, and then I'll figure it out, figure that out.
Yeah.
And then
Yeah, like with the quadrupeds and the bipeds, they'll have a safety harness, right? Like a safety cage with a
oh,
rope.
you can do that. You put a rope through it, now you're.
It's not a bad idea.
That's a good idea.
Tether to something until it gets its sea legs.
But you could suss out problems, when it's safe, and it's safely held, right? But then eventually you have to put it on the ground and.
Maybe build some sort of a rib cage to protect it if it does fall.
Oh,
Yeah,
a roll cage.
Yeah.
yeah. It's gonna be a very exciting couple of weeks once I connect up the commands that tell it to move.
Swimmers.
Oh, swimmers, like
Yeah.
the
Little kids.
the
swimmers.
body balloon?
Yeah. Put a noodle.
Well, thank you, Alan.
All right, thank you.
Right, so up next is Ryan. And just an announcement, if anybody has to show themselves, and if you know, so I can do this.
Yeah, so this is kind of a team thing.
Okay.
We're talking, I don't have a video shared, so I can send this screen if that's okay.
Oh, yeah, if you turn on your camera, I'll give you spotlight so that it.
Okay, so we're talking about the Robomagellan, and so this is our foray, and I'm gonna talk about one piece of it, which is the cone following part. So you've got here, we've got 3 cars on here, these are the 3 different entries. We've got blue bot, clear bot, and B bot, so the theme. Kind of a funny story, we were supposed to be Team Go Robot, they kind of Team Go,
Like GoBots?
yeah, but when my role was to be Robo Nerd, but their registration process was so bad, our team name ended up being Robo Nerd, and we just went with it.
Yeah, they had names of robot and team name, and.
Okay, so what is Robomagellan? It's a robotics competition where your vehicles navigate through outdoor environments. It's kind of a funny thing. We thought it was going to be all pavement and asphalt, and we looked at the map of where it was at, like there's no grass anywhere. So like we're ready to go. We got turned out it's all grass and trees and bushes.
Now, did he actually reach out to you a week before like he said he did?
No, absolutely not. No.
Absolutely.
Yeah.
Anyway, so you get GPS waypoints, and there's these cones like you see here. And your idea is to maybe touch some intermediate cones and try to touch the goal cone. And it's through a varied environment. This one was held as part of the 2024 Robo Games in San Jose. That was at the San Jose Convention Center, we thought. But this was actually outside. It's like a quarter mile away at some park somewhere that we just commandeered. And you can see Justin and Seth standing there, and then that's a B5 robot there. Okay, so here's a small part of the rules, and it's part of the rules we're caring about here. Start, destination, and bonus waypoints are designated with these cones. And there's a standard for the cones. They give you the dimensions for these cones. 18 inches by 11 inches. And I didn't realize they all have the stripe on it also. So you can kind of count on this being the form factor for these cones. Your robots must touch the cones. Like getting near a cone doesn't give you any points. You got to touch the cone, not knock it over, not slide it across the
Does
street.
they have an arm that reaches out?
Nobody has.
But one of them had really wide whiskers.
You can have.
Yes, you'll see we had some form of whiskers, but it was, let's touch it and then stop at the end to them in the course. So but this is the premise, like we've got these cones somewhere and we're gonna get the coordinates for them and we're gonna go find them and touch them through this very terrain. You're given the coordinates before you start, but that's kind of nice. You get approximate coordinates. He drops off the right-hand digits, so it's like within 60 feet or something.
That's huge for.
Not allowed. Not allowed. No RTK. Yeah, that's actually part of the rules, no RTK.
But did they allow you to walk the course before the first?
Very briefly, like, it turned out we went first. And we had like, it took us to the course, but it's gonna be around here, you have an hour to go get your stuff. Got our stuff in, the cones are out, and we barely had time to punch stuff in. It was very, very fast. But it was kind of good, you don't wanna just people mapping gross details of everything, so. Now we know what low level is. It's going to be like, here it is, here's your coordinates, go. Almost like that. So since we all have to talk about the robot stuff, like these are the robots, here's the stuff on them. They all have the same Traxxas / RC card base. We took these kind of nice RC cars and started modifying them. So we have a good mechanical base. Teensy 4.0 is just a standard microcontroller. It's fast. Orange Pi 5D single board computer is a lot like the one you're just showing us, but it's a different brand of the rock chip. Octa-core. It's
Okay, probably the same 80s, 50, 35, 80s.
This was a whole
same chip. Yeah. 6050 IMU, a GPS, a magnetometer that God knows what we got. Did you order and get something else? It's just what would happen to us. We have custom Hall sensing on the front wheels. We have a bunch of magnets, so we can tell within like how far the resolution. A few millimeters resolution on the wheel, so it's not like thousands, but it's pretty good for this. We have the OPT light cameras, and I highlighted it. That's kind of like the topic of this talk. This is using the OPT light. They have brushless motors, and on two of them we have motor sensors that can tell us like the position of the motor, and when we don't. So we're kind of like there's slight differences between the cars. So here's the overall strategy. Navigate to where your phone is, number one. Number two, get the phone inside of the camera. Number three, use the camera and LiDAR to guide the car to touch the phone. And so that sentence is the topic of today's talk. That's too many sentences. Then we've got the sit tight feeler, which didn't work out so well. I'll show you that. So as we get close enough, the sit tight is supposed to touch it, and we back off. So as long as you get close, you're okay. We thought. And then repeat that for each cone. So that those same steps, find it, nav to it, find it, go to it. So again, just concentrating on that, like we've seen the cone, we're trying to get to the cone, that's the sweet spot. So these are my opinions. So you want the car to go quickly to the cone. You don't want to like inch along, trudgingly. You want to go fast, and you also want to stop on time. You don't want to knock it over. You don't want to get stuck. A lot of the contestants knocked over the cone, the car resting on top, and kind of this motion that was kind of fun. Yeah. It was funny. And then so we don't want to do that. We want to like get to the cone and be stopped in a timely manner. We see it. We have this fun. We see the cone in the camera, and then we showed you before setting this fantastic object detection for cones. The small plate detection, which is nice bounding boxes. But that's in your camera. Where is it in the real world? So that's another problem. Like, where is it? And then the other thing is, when you get close to the cone, like the camera's no good anymore because it's the big orange blob in front of the camera. So we switched to LiDAR just in time for that. Here's where we get to math. So again, I'm going to challenge you guys to math. So I apologize. If you like math, great. If you don't like math, thanks, bear with me. So this is like, okay, how far away is the cone? So we measure so many pixels, right? So the cone is so many pixels high, so many pixels wide, and it's somewhere in your image. And we want to know how far away it is. Well, I know the field of view of the camera. So they're giving the horizontal and the vertical field of view. So I know like maybe it's a 48-degree vertical field of view. And I've got, say, 600 pixels or 1200 pixels. And the cone takes up 100 pixels. So I can do this math. I can say, well, this theta, the top of the cone to the bottom of the cone, is the number of detection pixels divided by my image vertical resolution, how many pixels it is totally, and then multiply that by the camera field of view. And that would give me this theta you're seeing in that picture there. So now I know the angle, so I'm getting closer to knowing how far the cone is away. So it translates into something real world. But I just got theta. Now, here's the hard thing. So remember trigonometry and triangles and everything, so I've got like, so you got the blue triangle on top, it's a right triangle, you got the bigger triangle. So I've got the theta for the big one. If I take half the theta, now I've got a nice right triangle. So now I can start doing my trigonometry. And everyone remembers trigonometry, one's good at it. Nice. So tangent of theta is opposite and over adjacent, right? So I've got a nice little diagram here. So in this diagram, opposite is h/2, and adjacent is this d that I'm looking for. This is what I'm at, that distance to the cone. So I've got tangent, if you look at the lower left, tangent of theta 2 equals h/2 divided by d. Flip things around a little bit with arithmetic, and you got d, the distance to the cone, is h/2 divided by 10 of theta over 2. And you want radians, by the way. All your functions take radians. But no, and okay, so sounds good. It turns out I was shocked how well this works. So there's other ways to get distances. This is working really, really well. Yeah.
Can't you just, use a predetermined size of your bounding box? If it's smaller, then you move toward it. So you know, based on trial and error, how big the bounding box should be.
You've got limited resolution.
Yeah, well, no, it's more than that. So I just don't want to know if I'm close enough. I want to know how far I am because I want to speed towards it. I want to slow down gradually. And so I need to
Just
know.
keep going until the bounding box gets to the right size.
Yeah, but I'm not going to go constant velocity.
Okay.
So I'm gonna, and I got another slide for that. So, like in your car, you can go park, right? You can go 30 miles an hour until you get into the parking spot. And that won't work. You can go 30, 20, 10, 5, 3, that's what we're trying to do. So that's why, yeah, you could do it. By the way, there's a simple way to do this. If it's to the right of this, you turn right. If it's to the left of this, you turn left. If it's bigger than this, you stop. If it's smaller than this, you go. But there's definitely a way, simpler way than what I'm showing. But it won't be this high performance way. So we're trying to get like more high performance thing. Yeah.
Maybe you'll get to it, but the OT stereo disparity with fused with the depth. So is that not
We
good?
just didn't try it. We just didn't
Oh,
try
because
it.
I've used that all the time on my orange stuff.
And I'm sitting here, I've got the dimensions, we tried this. Oh, it works really
Works
well.
fine, so
Done.
why bother with the other one?
Done. We're gonna revisit that later for other reasons,
Okay.
but for now, this works. And I'll show you how it works. It's surprising. What is that's what it is.
It's the thing that's here,
Kind of had things, my slides got to the wrong order somehow. But here's detecting the cone. So here we've got Foxglove and I've got a cone, down my hall somewhere. It's kind of that big. And so I got the bounding in the lower right picture. I've got the bounding box on the cone and I've got my certainty, 0.77, so it's probably a cone. And I take that information, I create a marker, and in this case, the marker is a semi-transparent cylinder. And so in the upper right image, you see that cylinder overlaid on the cone pretty perfectly. It's like that's this right of combination.
So in your image, you kind of have like that mirrored thing going on because of your clear or your door being shiny.
Yeah,
Does that throw anything off with
Yeah.
it having it is?
sometimes, but his detector is really good. So mostly it gets it right, but sometimes that or putting something orange or white behind the cone will mess it up. And so, yeah, it's mostly good though, surprisingly. And on the left, you see my LiDAR map. So you can see that this is the hallway and that, again, that's that same marker, now it's in the projection. That's where it is. And you kind of notice there's no LiDAR. So the LiDAR isn't really detecting it at this distance. So I've got all these things going on based on that map and that stuff I was showing you.
You put, that's a actual cylinder and 3D cylinder
Yeah.
that's in your, like a point cloud or, I mean, or
There's something called a marker.
marker.
In ROS,
In
and you
ROS.
say, okay, I'm gonna put a marker here, it's orange, it's got this translucency or trans alpha value, this top big, this wide, this orientation. And these tools know how to render that. So, I mean, it's pretty cool, it's like, how do I know it's correct? Oh, I looked at it, it's good, it's correct. Instead of measuring everything all the time to get the right answers.
But that's for visualization, that marker.
Yeah, it's this, actually kind of.
Or does it actually work in the, is it used in the actual real finding the cone?
It turns out I was using for visualization, but it was also handy. I am using it now, and I probably shouldn't, but I'm using it as a called location right now.
Oh, okay, so it is,
Yeah. And so here's an example. It's the same kind of setup. Now I got a video of it. I got two cones. I don't know, it's still the same thing, reflections and dizziness and all that stuff. Got the two markers on the map, and I've got the cylinders. So let me just run this in 14 seconds. I drive the car around a little bit in the house. And you can see the updating is like pretty dang good.
Interesting, the LiDAR is not picking up the phones very much.
Yeah, that's why we're using the cameras. They're slick and this and that, and I got the cheaper LiDAR. I don't know if that's part of it, but that surface is not LiDAR friendly.
All that energy.
Yeah.
The airness.
Oh, what?
When
Yeah,
you're shooting down another jet,
Yeah.
your infrared sensor gets saturated when you're near the target.
Ah.
And then you have a real problem. You don't know how far away the target is.
LiDAR.
And IR is filling.
Ah.
So that's a really common problem. I don't know. Why is it? Why is what you're doing? All the documents and papers and everyone.
Yeah, so I haven't, this is a problem when the cone fills too much of the display, I can't measure the balance anymore.
Yep.
But now it is close enough to the LiDAR.
Yep.
So I switched to LiDAR.
Right, we can't use those.
Okay, John.
Let me go back to this. So I found the cone and now I'm able to see it in real time. I'm a perfectionist, right? So I'm getting these. I'm clocking 10 frames a second, which is pretty fast, but the car is going, let's say it's going. So a tenth of a second might be a foot or something. It's pretty fast. So this is, yeah, it was overkill. But it was a little jerky, and like the acceleration was getting a little jerky, and I want it super smooth. And so there's this thing in ROS where I can say, well, it was here in relation to base link at this time. And can you tell me where it is in relation to base link right now, or in relation to something else right now? But what I would like is to know the location in relation to my front bumper. So I've got this real little piece of code that says, well, now I care about now, and that's now. I care about when. So that's when I took the image of the column. Okay? I want the frame that I care about now is my front bumper. Like, okay, where is it compared to my front bumper? The when for the images when I took the image from the camera. So I got this average time step. Okay,
That's the
frame.
frame.
Average time snap right there. And I get the frames of these things. So, okay, well, this marker was from the frame of the camera, and I care about the frame of the bumper. So finally, this lookup transform will do all the math, and it'll find the common point in time, and it'll tell me, oh yeah, so where this thing that you saw a tenth of a second ago, here's where it is now in relation to your buffer hardly. So this is really cool. So it is, I think you really need this for higher performance stuff. If you're willing to go constant speed, don't need it, but the faster you go, And then we have, what would you call it when you get close to the
Endgame.
target? End game.
Endgame.
So I'm doing great, getting close to the cone. Now it's saturated my screen. It's just filling my screen. I can't measure the bounding box anymore. That's a problem. And another problem is maybe it's like a little bit behind that door. And so it looks narrower or it looks taller. And so I get like 3 different kinds of measurements for this cone. One of them is how far it is away based on cone width. Another one based on cone height. And another one based on the LiDAR distance. And each one has its problems. So for the obscured faces, it'll seem further away. When it's obscured, it'll seem narrower and it'll seem further away. So I take these 2 visual measurements. I take the closer of the 2. So if you like block the right-hand side of the cone, it's still just as tall. Or if we block the top of the cone, it's still just as wide. So we're going to be good. And then when I get within a meter of the cone, I will say, well, it's close enough. Forget about the camera. LiDAR's got a great lock on it. Just look at the points in front of me and use that as distance. So for me, the trade-off is like at 1 meter. The 1 meter, I switch to the LiDAR. Okay, here's where we get to this high-speed stuff. So what I want to do is I've got a certain speed I'm willing to travel, say 10 miles an hour, 15 miles an hour, whatever it is. Like where if I crash, the car might not get destroyed and it might not go somewhere. Like that's that speed, right? But as I approach the cone, I want to slow down with a constant deceleration until I get exactly to where the cone is and then I stop, right? So I won't go to 30 miles an hour to 0 miles an hour in the parking spot. I will actually decelerate it. Now this is more math because, well, I've got the acceleration, I've got velocity versus time, but I don't know how far away I am. I don't know the time. I know the distance. So I got another curve and more math, and it's real tiny math, so I apologize. But this is when I look at how fast I want to go based on the distance from the cone. So if I'm, for the max velocity, I'm in that flat part of the curve. But as I get closer, then there's the kinematics. I these. Remember, g equals 1/2 at squared. That's your distance for constant acceleration. I've got v equals at. That's how fast you're going at a certain time. Those are good, but they don't give me velocity for distance. So I do some math. I put, one and the other with substitution, and I solve it, and I end up with velocity is a square root of 2va. So what this means is given a point away from the cone, I know how fast I need to be going. And it's tunable based on the acceleration I want. If I want to be really aggressive, I have a high acceleration. If I want to be less aggressive, I use a lower acceleration. And I can take this velocity and hand it over to my CMV bell message to basically tell my motors exactly how fast they should be going right now.
Is the A is the A that you are decrease is the A a
Yeah, it's deceleration.
the negative.
Negative A.
So
Right?
you choose an A.
Yeah, I'll choose an A. So like, let's say in my house, I've got that shiny floor, which always has a little layer of dust on it. And so the A has to be like 1 meter per second squared, right? It's really slow, like a tenth of a G. And it literally starts sliding after that. If I'm out on the street, maybe I could use like a 0.5 or something, or 5 meters per second squared. So yeah, I choose that, and like depending on how you choose that, it'll drive very aggressively or very smoothly.
So yeah, it's a negative.
Yeah, it's a
Decel.
negative. Yeah. And here's so here's the same hallway. I moved the car off, so it's not actually pointing at the cone, it's pointing somewhere else to show you that this all works. And it's using all these algorithms are the same. I think I got max velocity 3 meters per second, acceleration 0.2. Good. a second to start. It kind of like zooms along and it slows down. Nice, nice, nice. And I set it to stop 15 centimeters and it stopped like 14.8 centimeters. So, yeah, and
That's about perfection.
yeah.
Wow.
Better.
Yeah, but it's fun to do these fingerings and things. So good. Now, look, I'm out of time. I got a few more slides. Should I generally keep going or?
Oh, yeah, go ahead.
Oh, okay, yeah. Okay. And now we're up to the competition. So that's all the stuff I did. Now, how did it turn out? Not as good as I understood that's right? Right before the competition, he gave us these pieces of paper. It's like, here's what you're up against. So you got these pictures of the cones here. We got Google Maps overview. I can tell you these cones are not exactly what they're like talking about. I don't know, they're not perfect. And here we have the lat mons of the start cone, the 3 bonus cones, and the goal cone. So this is what we're saying, would be like punch them into our program to do whatever we want. Here's, I got 2, and so they're out of order, but here's almost touching this. I turned out I couldn't even touch the cone for different reasons. Like this stuff works with trust.
On your mark, get set.
So follow waypoint. And yeah, tons of people now what you're going to go on.
I thought it was further up here. Anybody still see it?
I was looking for yeah.
If it doesn't find it, it's okay.
How's my name? Go into the circle, start flying to the phone. You see a zip tie in front. It's bent over.
Watch out. Oh, come on. The thing got pushed down.
Too unaggressive.
Come on, zip tie.
Yes.
Zip tie.
What if I?
The zip tie got pushed down. So it would have touched it. Yeah. So now it's going to go, should go to the next one.
Wheels are spinning.
Oh, are you kidding me?
I did not like.
Give it a second. Maybe it'll come a new path or something.
Little golden
Yeah.
balls. Oh.
Yeah, so it's.
But that's, can you hold up your card, Justin?
There's a solution.
Yeah.
Oh, you got it.
Yeah, that's the solution. So Justin found those, he's already spec'd them out. These are gonna work pretty
Did you
well.
put those on?
Yeah, that's Justin's car. I got
That's
my
how they
list.
work. No, these are new ones.
Sure,
Those are the new ones. So. This is more like what we had. Yeah, okay, because yours were a little bit, these are significantly smaller.
Yeah.
And this.
Oh, yeah,
Oh.
that's what I have too.
Wow, yeah.
And his were even smaller, smooth street tires. He was optimized for street racing.
Yeah.
So his just spun like crazy. We weren't prepared for this.
We all thought it was gonna be paved routes. We all thought the thing was gonna be paved.
Like I said 5 months ago.
Closer to the cone. Yeah, it's.
Show me that later. I don't know. This is a longer video. This is the winning. This is the 3rd place run. You see if it's not perfect.
Yeah, can I get stuck here?
Wow.
Here. Go, go, go.
Go, 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 go.
It's
Come on, come on.
That's right.
That's a slash, isn't it?
Yeah, it is.
I know that RC car.
Oh yeah, he raised it up. Big fucking car, dude. I'm very happy with that.
34 meters. Took a while to get
I'm very
started.
happy. If it hits something, it'll just keep going. It'll go through it.
Oh yeah?
It might hit this pole, but it's okay.
Oh!
Damn.
That was your LiDAR, right?
I turned the light off. That was pure luck, huh? Pure luck. Oh, but
Oh,
sweet. He may actually make that curve. Oh no. It'll make the curve. It'll make it. Go, 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 go.
let's go.
Oh, that was the walkthrough that helped.
We're like 10 meters.
So much crap and everything.
We're 8 meters. Come on, do not disconnect. Come on.
Okay, it can go. Keep going.
Faster, faster, faster. Oh, something, go somewhere.
Yeah, it's gonna go.
Oh!
Okay. It's gonna get it. It's gonna get to the cone.
Here,
Yeah.
Look over here.
tries to go in the circle to find it again.
Then it's gonna. Okay, circling. It's gonna see it in a second. No, no, don't. No. And stuck. Oh, error.
Error? What's the error say?
Yeah.
Missing positional argument seconds.
Okay, it's done. It's
I
done.
guess I was gonna run, it didn't, it had Python coders. But anyways,
Oh, it was a Python error.
yeah, I called another function with the wrong parameters.
Yeah.
But
But
it was,
only in this case where it was,
yeah, only after they'd gotten like off the end of the world, and then it was probably gonna try something else, like backup or something.
oh,
But it was already gone, it was already dead.
How many people entered the contest and did you learn anything else by observing other people?
Yeah, you use a big car. Everyone seems to be really using GPS. I mean, GPS is good enough in these outdoor things that don't worry about SLAM and all those technologies. Yeah, those are the big ones, and the different feelers are like the big feelers. I had big feelers, big feelers, that's it, I find it better. Yeah, but one of them you couldn't get tough enough to even start, and the other one has such problems with grip, it just moved not much.
Oh, okay.
Yeah, so that was the best run, but next time let's.
There you go.
How many people entered?
Is your camera on a turbo?
No, it's
down
not.
with
So, yeah, that's the drive.
It's like the opposite is one of the bigger problems. All kinds of stuff in the way.
So mine's.
Like the one not this year, but the previous year, they had the code behind them.
Oh, yeah.
It's like a.
Oh.
In between.
Yeah.
Yeah, it was like, how do you?
Well, this one, there was one of the bonus cones, this is firecracker, this is, poles, and it was in between two of those, so. Nobody went for that. And it was, one of the things I learned is like, no one does great, even the winner didn't do that great. So, I mean, there's a lot of room for everyone to improve, and that's kind of fun, or like, they're the, really the cutting edge, at least for the people that were there. There were what, like 12 teams?
was it that many?
Yeah, there was like 12 games and probably like 50 people gathered there that made it to the park. Something like that, 30,
30, maybe 30.
yeah, it was those kind of numbers. Okay. So, like, oh, no, I got more slides.
Reach out with them.
Sorry, Chad. Eating your time, I was gonna warn you that kind of time. Postmortem, this is important. Need to practice on grass. Number one, I was doing manual waypoints that hey, go this way. That worked fine. I think we'll do that again next time. We use the Motoro DOM. This is my bug for the speed of the car. And one of the cars didn't have Motoro DOM. It was just, and so that was a big problem for Justin's car.
Sorry, Justin.
Or didn't have.
For waypoints, do you like carry the car around to get the waypoints, or do you have a separate GPS that you carry around?
Maybe it's another talk, but I took Google Maps, basically, I clicked on it and map is, I say, go here, 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 here. And I just captured that, I go over to capture that, and I plug that into my phone.
That's the way, I think.
Yeah, I know that worked really well. Google Maps is perfect. Like, all the points are dead on.
Yeah, the map they give you at the event, you throw away immediately.
Yeah.
What's the resolution on GPS? How,
So I think
To
here,
find a
we were
waypoint.
getting, I think it was clear sky, no buildings, like 2 meters or something. It was pretty good. You think 5?
I know. Commercial GPS is 5 meter accuracy.
Is that plus or minus or the entire band?
It's 5 meter. If you have a post, you have a 5 meter circle.
So 10 meters.
But typically,
I think-
shop is a meter or two.
Well,
Yeah.
There's no restrictions on GPS anymore.
Was
They don't,
5
they don't
meters
block
from
you
the
out.
point?
Like you get
So-
30
So,
miles.
I don't know,
There's a lot
there's
of,
something going on where we're getting better than that. I don't know what it is.
there's a lot of stuff I'd like to say.
I hate that. Okay.
There's a reason they can fly a cruise missile through the floor.
Yeah, that's right.
Well, the government has.
But it's been getting better for
Well,
terrestrial.
maybe it's changed since the last time I was messing with it. Yeah.
better accuracy.
Oh, yeah.
Archie,
You
you
can't do that.
you can't
Like,
use
so that GPS.
There's other technologies, I think. The satellites are now even transmitting some of the corrections that RTK would have given you, so there's other things going on. And I'm not sure if we're using it, if we are, it might be cheating, but it's not on purpose. Okay, so, recovery of behaviors are very important, so we got stuck on a tree branch, we got stuck in deep grass. If I was driving it manually, I would like, and I would have gotten out of that stuck. And so we need a program in those recovery.
Behavior tree.
Oh, maybe. Let's talk about that. I don't know.
They could theoretically also make you guys go on like bark or gravel, or like literally
Absolutely.
anything,
Absolutely,
sand.
sure.
You need paddle tires.
Well, I mean,
I
I think that the guy, so Kath is the guy that does the course. He knows the kind of cars people have, and he tries to like just barely push the limits on the cars. So he wouldn't, put us into the dunes or
Yeah.
something.
No, it's gonna be a a region, a park, like a park
Yeah.
environment, or even street environment.
Yeah, and so one observation, we turned off the LiDAR for obstacle avoidance and it didn't matter. So it was just pretend like there's no obstacles and go and hit something, you cover it. It's the way to think of it. Networking was a problem. I bought a little router, like so excited that I was prepared. I got this thing all connected and good, and it would lose connection occasionally. So we switched to phones, and their phones are great. My hotspot, my phone, I couldn't get the IP address of my robot. We had to like plug in HDMI. So solving the networking for being in the field is important. The wire time.
Big whiskers maybe.
But you know what I'm thinking too, is I know the way you have it connected, it's in, like, it can naturally curve down, right? Because the way it's connected this way.
Yeah.
So if you had it somehow sideways, zip ties don't bend that way,
That's a
right?
good point. Yeah.
So like,
yeah.
Yeah.
it wants to bend
So use
the
a better
way,
zip tie.
it would
I
change the
change
orientation.
orientation.
Yeah.
So it doesn't want to.
It won't wanna bend down. It'll go, yeah.
Not set up grass.
Yeah.
Yeah.
Typically, it's not gonna bend.
Oh, got it. It wouldn't have caught on the grass in the first place. Yeah.
So now that's deep grass, I think it's.
Yeah.
Grass compliant.
Have one going each way.
The Martin,
Yeah.
the Martin Mason team, they had, something coming off the top of the robot, which was these wires
They
that
look
went
at
way-
span like 3 feet.
Yeah, they go
Yeah.
upward and they're curved up, so that seemed like a good solution they had, those whiskers.
Hugging. What test, more field testing before you go out there. Now we didn't have time, so this is not messed up, but we didn't have time. So now if we're doing the SIG, then we can test ahead of time. That would be awesome. Last one is not all obstacles show up in LiDAR, so your LiDAR isn't that useful. Because you've got things that are this high, things that are this high, and your LiDAR only sees exactly that high. So that's not good enough. So we either use the camera, like trying the OP disparity maps, or just drive by braille. One of those two. Because the LiDAR is not enough for obstacles.
So you might want a front bumper like I do, that would help.
Yeah. And there's a picture of the before and after tires I jumped.
You got it.
I kept that one.
Question, what's the networking used for? What do you use that for?
So we need to command the car to start. We need to calibrate things before the race. So all the processing's on the car, but just like you saw, Seth walking around with a laptop, oh, it said this, so we can.
Okay,
see
so
what's
you're
going on.
monitoring it.
Yeah.
Telemetry.
So we start it and we monitor it from the laptop. So there's, but already we have like a 3 or 4 step startup process. So it's not system view yet. We're doing it next.
And some people put a button on the robot to do the final startup. If you have, that's
Well,
what,
we had a switch on the controller, so like mine, I would set everything up, it was just ready to go. So I just took the car and the controller, I put the switch and it goes.
yes,
But before that, you used your.
Yeah, before that, I set it up to go.
Yeah, so we have the same strategy, that same switch, the handoff auto switch. You have it in the off position, you switch it to auto and it starts going.
well, that's what I was thinking of doing.
Yeah, that works well.
When you go in that, from manual to auto, then it starts the program.
And that's it. So everyone always asks for, do you have the source code? Yeah, of course, I have the source code. A couple of links to the Robomagellan, Robomagellan, if anyone's interested in those things. And a link to this deck. I don't know if that's useful or not, it's in the deck, but this deck is online also. Oh, good. Good.
Yeah, you're up. All right. Yes, I'm gonna have to move along here.
Jim, if you could turn on your camera, I'll spotlight you.
It won't take too much. Andrew. So my talk is, they always want you to join audio. So in the same effort, I have been building sort of a robot RC car for Robomagellan, but I didn't get far enough to actually have it really work for the contest. So what I've been focusing on is the ROS part and navigation using ROS with the robot for indoor or outdoor with LiDAR based. But I have the GPS software, I haven't done all that stuff. So what I'm going to talk about today is kind of before the earlier stages of what Brian's team went through is hacking your RC car and bringing the MicroROS into your microcontroller. So this is like the second talk I've given on this. The first one, I talked about sort of just hacking it from the very beginning to actually get an RC car controllable by your Arduino. Yeah, here's some because the bill of pictures. Quite so this is you can see the Ackermann steering here. Should be about there. So I was going to some other subscriptions and publishing, like the standard things you need to get the robot to move where you're telling it to. That's built into the, to this code base. I'll show as much as I can of that. So here's the type of base and hardware specs. It's Teensy 4.1. This file called Lino base config is your friend. It has the where everything is configured of your bot, including, like, for instance, you'll see here it says Ackermann. This is my base. It's an Ackermann base. I had to add this in throughout the code, merging in my friend's code as well as, you know, modifying it for mine. And then ESC, you have these other options, different types of motors, or motor drivers, for instance, like ETS 7960. And then there's controls in here for the encoders, like a PID control thing. I'm not currently using that, but that I will eventually when I add that in. And then there's all these different statistics or specifications, physical measurements like wheel diameter and distance between the wheels, and PWM. And then the steering was added too. Steering, this is for Ackermann steering, with maximum turn radius and the full the different PWMs for the steering servo. And normally, if you're doing if you're not using an Ackermann, we don't really use these because it's differential steering, so it just rotates the wheels at different speeds to do the steering. And let's go back. So and so this is what I just showing you: the steering specs, ESC, and then your pin assignments for various things are in that file too. So now I'll show you just how I went through those different line items for configuration. The ESC, I kind of rewrote a module to handle my particular one with the correct PWM, neutral versus forward and backward. And then using the servo class actually worked fairly well for that ESC, for just generating the PWM signal. And this is a standard Arduino server class. And so that one worked pretty well. It's not even much code to do it, but like right in here, this motor interface, I'm sorry, default motor, this section here is ESC. I just have a servo for the motor, a pin, frequency is sort of optional, but, and then my forward, reverse, and then neutral, PWM neutral, and initialization. You can change the frequency of how often it's and then breaking. It's pretty simple, but what's nice about this is it's very highly configurable, and so you can use different motors. The next one is Ackermann steering. That's a new module. There's a few things there you have to do. You have to convert what ROS sends, which is an X velocity, a Y velocity, and angular velocity, and into a steering angle and X velocity only, because that's all the Ackermann robot can do. It converts. It basically is going to be driving in some sort of turning radius, and so these values, or the angular velocity, gets converted into that steering angle. And what's interesting also is if you're not moving, you can't turn in place with an Ackermann vehicle, so the whole spin option is not available, whereas ROS will, instruct robots to spin, in other words, rotate in place if they have, the ability to do that. But I have to disable all of that in my ROS stack, so that it will never try to spin. It said, well, don't do anything. And even when, the robot has a 0x velocity, X, by the way, is straight ahead, straight off the front of the product. If it has 0x, then steering angle is irrelevant. So I turn off the steering if the car stops. That avoids the steering, the wheels from turning a lot when the car is stopped, if you don't need that. And then the modified kinematics, which is essentially the result of this. Kinematics is how basically this conversion of the velocity into wheel rotation, essentially, or RPM. If there's any questions, feel free to butt in. The next thing is the remote control. I wanted to add, so I added a module for the Traxxas remote control. And that's this portion here. So I added a simple class here to handle the throttle, the steering, and e-stop. So the Traxxas remote control is the one that came with the car, and it sends signals to the receiver over 2.4 gigahertz RF signal. And so this module handles that low level or that handling of what I do with what's coming off the remote. If I get a better remote with more channel, or if I probably should replace this receiver and remote control and get more functionality here, like actually a switch on the remote control to change from auto to manual, for instance. Currently, this can't do any of that. I've only got 2 channels. So essentially, the e-stop is if it's in auto mode and you let go of the throttle, that's an e-stop. And in manual mode, the remote control works normally, throttle plus steering. In auto mode, everything is just the e-stop function. So that's that new module. And then I added the bumper publisher. So this, when I say publisher and subscriber, I'm talking about ROS topics. For those not familiar, ROS uses messages published on what they call topics, and different elements in the system can subscribe to these messages. So essentially, if my car is hitting something, it will be publishing false repeatedly until it comes unstuck, unpressed. And so that code is added to this code base that wasn't there before. And again, it comes with a lot of stuff to begin with. So I had to add only things that were specific to my build. Another thing I needed to add was camera pan and tilt servo angle. So I subscribe to the pan and tilt angles. And so when I want to change the angle of where the camera's pointing, I publish an angle. I call a function, or I even have a command line. I could say from ROS, and it sends this message in, change your pan to 45 degrees, and that is handled in the MicroROS. So there's the IMU. I use the 9250. This support is built into this code base. So, and you can use different IMUs. There's a few different choices. So, unfortunately, there was one problem. It didn't work, and my particular 9250 had a different vendor code. And so I got an LED blink error and had to track that down and add the new vendor code so that it would initialize, it would identify my particular IMU as a valid one and not give an error like that it didn't initialize. Next thing is the wheel and motor driver. This is the TDD. Oh wait, yeah. So I don't have this currently. The other guys did, but the code is all there in this system, in this off the GitHub for a closed loop control of your motors using a base based on the required RPM versus measured RPM. So this code is in there as well. So when the ROS upper system sends what's called the command velocity, when you publish, the way that ROS system will tell the robot, I want you to go, is it'll publish a velocity like X, Y, and rotational. And those come over via a message. And then your code has to tell the motors to move by giving a PWM signal. So again, the thing in robotics is whenever you expect something to do something, it rarely does what you expected it to do. So the same thing goes with these motors. So mine is currently open loop where it just sends this a PWM signal expecting it to go at the rate that that's supposed to go, but in reality, it won't do that. And ideally, you have this closed loop, so it will measure the error and compensate, and that's the standard PID. I won't, talk about that anymore here, but that's a very useful thing to have. The other, so for tips of debugging and logging, before when you're writing this code, you'll want to know when things go wrong, and if the MicroROS initialization has not happened yet, there's no way to send messages over the serial port. By the way, this is connected via USB serial, so all the messages are going over serial. Before MicroROS is initialized, I need some ways, and there's a LED on the Teensy. So the code uses already, it's there. I didn't have to add this from scratch. They had an LED blink code or LED blink routine, and pin number 13, as usual, Arduino style, is the LED. And so, like, I got there's a function for it that is used for when there's an error, and it is a blink count. Then it will blink so many times and then wait and then repeat. So I got a blink of an error blink of 2, and that turned out to be the IMU. That was that problem I had to track down. And then you also have some blinks when things succeeded. And so if it blinks just twice and does nothing else, then goes dark, then I know everything has been initialized. And so after MicroROS is initialized, then there's a convenient logger class, and you call this function to log a message, and that goes over it publishes over to a thing called the ROS out, ROS2 topic, and that's a common place where messages get sent, and you can subscribe to that from your PC and see what messages are coming through. I'll show that in a show and tell if I have the chance. And then here, one other tip is VS Code with remote SSH runs a lot of server code on the Pi. if you do a PS-EF, you'll see 20 different processes running. So I use this thing, remote SSH kill VS Code server, to clean that up. And also called disconnect the VS Code, but disconnecting doesn't kill all these things. So they eat up some CPU time. I don't have a lot to spare. So you just kill those when you're kind of done editing. You want to test the robot in optimal performance. And so that's the end of those slides. And going back to the main code. So here's the main structure of this is a firmware directory, a single firmware file called firmware.ino, and then there's a library, and you can see here library as encoder, IMU, kinematics, logging, motor, and the steering I added, and I added Traxxas control to that. Most of these came with it, and then you modify as needed. So here, this is the main. But one thing I might point out here is the code that came with this system handles the higher level, or essentially the ROS connection. Oh, wait, I forgot to go to my. I won't go to the code now. I'll go to the web pages I prepared here. So there's your example of Ackermann steering. How it this steering angle is what we were talking about in all that code. Now, yeah, I wanted to show you. I prepared this this thing here. So the overall design here is you have a robot computer, and you have the micro computer down there. Let's see. All right, so now, so those are the two elements. Now I bring in different things. The microcomputer running the ROS libraries, which I told you are pulled in automatically by that build, the platform IO configuration. So these are the things you need to implement a MicroROS system. And now let's move to the next one. On the robot computer side, we have what's called the ROS agent. And now the interface between these two is serial port. So the ROS agent is handling everything, the communication from the higher level computer to your microcontroller, and it talks to the library, or it talks to your system over serial, and that's how you get the messages. And you send messages back and forth. So inside here, I showed you various things related to the system. The encoders are there, encoder driver, which I'm not using. Then there's the kinematics and PID. I'm using kinematics, but not PID. Kinematics is required really for how to convert a velocity into wheel rotations, and then because that's what it does essentially, or steering as well. IMU is here, which I kind of hinted about, and then the motor drivers, and now, well, the last thing is the more higher level stuff, which we're not talking about today, but the whole nav system is above here. But I'm not talking about that, but that's where the agent communicates with the higher level loss from your robot with things like this, telling it where to go with command velocity and figuring out where it went, from your encoder, your encoders will give odometry, an unfiltered odometry, and your IMU will deliver orientation, acceleration, etc. To, to the higher level. Actually, this. So here you can see just a quick diagram of how, well, in this case, so this is the website for MicroROS. It's full of a very detailed documentation that you can look at. And then, I won't go into too much there, but they have a lot going on here, which kind of will explain a lot of the background of how that Reno Robot 2 actually works. But I'm connecting the Teensy to the Raspberry Pi, not the, right, in this case, this is the Raspberry Pi, this Teensy. Well, let's move to the next. So here's the my branch of the Reno Robot 2 hardware. So I branched, and this has a very good series of instructions for going through and also building your robot. You can see here the different wheel configurations. This is how your robot is set up. X, it tells you the axis of movement, how the motors would work if you have up to 4 motors. I only have 1 motor that controls all 4 wheels. And then here's the different motor drivers. I'm using this last one. Again, this is all about the options that this framework has. I'm using this option 250. And then here's some connection diagrams of how things hook up. Sort of like what mine, but I showed you that last time on my robot. And here's a similar diagram where you have your microcontroller, motor drivers, battery, etc. And then this is your robot computer with that upper level, higher level functionality. And so these are very good instructions. This will, I'll keep this in the stack here, or I'll publish all these locations. And yeah, the MicroROS platform IO, we're using that, and it supports all these different boards, so it's quite good. ESP is a common one people like to use, even the Raspberry Pi Pico. And here, let's show a video. So the Truckosaurus so far has 2 videos. Just to show, I guess, once you've done that kind of work to the low level, then you can get a robot working autonomously with the higher level navigation. You can see, so this is a map of a patio, and the robot is located here on the right. It's set different waypoints for where you want it to go. And then once you set it off, it'll start moving to each goal. And so this is jumping ahead sort of to the next talk, is about integrating navigation and how it all works to navigate to the actual on the map. Where and this map is now based on that LiDAR, so it's critical to have walls or objects of significant size for this to work. This won't work out in the video. You can see it. It didn't see that, but the LiDAR, I don't have anything other than the LiDAR here, working with the navigation, and the IMU, I guess, but this, this won't work for Robomagellan. This is sort of more of a in the lab or around a building where there's some map that can be made. And this is just an example of going to the, so I had set the waypoint there to finish off, or the final waypoint. There were a few waypoints that I had set to get there. And so, yeah, so it's past 12. Does anybody have any questions? I'll wrap up and do any more after lunch.
Thank you, Jim.
All right.
All right, so that'll wrap up for talks. We'll now break for lunch. Again, if anybody has yes. After or no, before lunch. Oh, okay.
Well, that's why we do the show and tell.
So far, I only have Jim for show and tell. If anybody else has a show and tell, let me know.
Potential, but only if I can get the videos to onto the computer.
Okay, I'll put you down.
Yeah.
Yeah, put me down too for it.
Well, somebody else can go first because I just did a talk.
Okay, so.
Just a moment.
Nice. Yeah, everyone who's connected to computers has a camera on the computer, that's what we see. Alan by himself, Jim by himself, we see. But that's, a little technical on just pride.
Oh, next one. That, I've never really, I don't know about the hand on it, but I never made one. It's like, some old one, like, toy robot called a rodeo had those, and I loved it because it could go sideways and go in any direction. So those are cool, but, and they require, yeah, some, in fact, I think that robot too had like neck on, I think it had a neck option interface. Oh, everybody.
Yeah.
All right, good seeing you guys. See you next month.
He hasn't been coming.
So yeah, those are good, those are good.
Yeah.
Yeah, good.
I need you to go find something.
It's just called the Yahoo Monster Robot.
Oh, yeah.
My mom told me it was seven growth.
I haven't used that one, but, you know, it's probably good, I mean, this I didn't need as control. You know, the RC car comes with, ESC.
Oh, yeah.
And you just plug it in.
Never on.
And then you hijack the RF signals, which is in high volt or 6 volt, whatever, so it's all compatible with your controller. So I can send servo signals, basically I'm unplugging.
All right, guys. So just a little quick round out the show and tell, sort of like this fun. At the end of last year, I ordered a robot dog and it took so long to ship that I got bored and came up with the Alfie Project. So right around the same time, all the Alfie parts arrived, the dog arrived as well. So I haven't brought him in yet because I only want to bring a one robot at a time. But this is actually, I want to enter in my go-to into Robomagellan next year, or at least do it locally here. So I have a really quick clip just to show you how fond my dog is of the robot.
Oh, I didn't know you actually had it on order. That's awesome. The one thing that stopped me, I love the dog, that's awesome. Did you figure out, can you program it? Can you?
Oh, yeah, there's actually multiple groups using the hack I went over a few months ago, and they.
And so it's works, it's solid, you can do everything.
Yeah, he did it. He's guy.
Yeah, so I'll start,
Can't say that.
I'll try to find time to start the Magellan as well, because I really want to get this guy off the ground, but. Yeah, I'm hopeful. I should be able to do all processing on board. There's one USB port, so maybe I can plug in a GPS. You know, but yeah, I thought it would be fun. Like most things, I don't plan on winning. For me, it's more about the experience, but. Well,
We're gonna have you go up and do this on a cone, would just be.
oh, just walk up to it and be like.
Yeah.
So you don't have, it doesn't have to be wheeled.
So about the go-to, just recently, a company put a flamethrower on it.
Oh, yeah.
And I was suspecting that they're using his tag to do that because the dog is not the price of the actual, the pricier dog. So I'm guessing they got the same dog, used it from having, put a flamethrower on.
After, it's really just when people get back from lunch, because we changed the schedule now, so.
Oh, yeah.
Officially, we end the meeting after the show.
Yeah, I can do brains on board. What I'm hoping is I do the onboard rock chip NPU for drone identification. So I might have enough processing to do simple, but yeah, there's always room for a fully fledged.
Because you wanna do the whole thing like. Yeah, the computer, the single board computer that you have, put it on the back, a little battery, and you're good.
Yeah, you're welcome to.
Well, that's funny. The
We
ASC
figured,
rock
yeah.
chip inside the dog as the one in the
But
board.
it's probably busy.
I'm not even sure. I haven't even gone through the crap of doing each shot to see what the utilization is. But
That's
yeah.
cool, because I'm like the only person that I know that
Uh,
know that has this.
1600 for, yeah, that's right. 1600 for the dog, 400 for shipping because reasons. So $2,000 dog. And if you get busted from customs, it's an extra $400. But for whatever reason, knock on wood, customs.
So I took that code and
So,
finally got it working.
out the door, 2,000.
So I'm publishing that now, so
Yeah.
this old.
Yeah,
it's
I'm excited.
End of life device, but, you know, it worked on all.
Yeah, that dog, the one he was just showing, not the little dog.
So cool. So it's.
Well, that's what he wants to do, and I might join, I might have two entries. That looks like fun.
You don't have to worry
All
about
this
that
search
graphics too much.
engine that publishes ROS topics for you, you don't have.
Yeah, it turns out all four models have the exact same.
I don't forgot, maybe you can
Open up, DDS interfaces, which opens
I
up.
just didn't know about it.
Even the charging pads, it's all wired up. You're like, I'm missing the speaker and I'm missing the little doohickey that does localization for follow along.
Try to demo this thing
Yeah.
forward,
I want-
right?
For follow.
Oh, yeah, you have a little transmitter.
Oh, yeah, you don't want that.
So, yeah, like people are even figured out that it'll even, as long as you handle the software, like as long as it lands on charging pads, it handles self-charging. Without buying the $14,000 one, $500 charging.
Oh, so it's pods are charging.
Not the pods, but
Yeah, I'll be here.
the nipples. Yeah.
Can it balance itself in 2 legs?
They haven't one locked down so far, that feature, because it's not super reliable.
Wow.
But I've seen some videos of it, like their promotional video, it's doing like the handstand thing.
It's amazing you can even get for $2,000. Eventually, you'll see those in toy stores and things probably, you know.
Yeah.
Well,
Wait, you said, my mind is slow. You said cyclone, that means it's using ROS internally.
It's using Cyclone DVS internal. Yeah.
But does that mean it's using ROS? The cyclone is one of the middlewares.
Yeah, it's Cyclone DVS, and apparently what they're doing is ROS compatible. I don't know if they're running a full ROS list or not, but it passes ROS messages. That's what it is. So yeah, probably ROS. Like full blown ROS. Yeah.
the controlling of something like that, so hairy, all the joints and everything.
Yeah, for the Robomagellan mill, I'm just gonna use the high level, so I'll give it attitude and direction, velocity, I'll let the leg show it all works on its own. So what got me really excited about doing it was that with all of this, these deep learning approaches to movement and motion and stuff, there's a small section of that for quadrupeds. And so the code they're using is 8 years old now, it's MIT's new code. But now that I have access to the full DOM, the opportunity exists to do some of these newer approaches to motion planning and movement that are super creepy natural. That's so good.
Nice. So are we gonna do lunch now?
I don't know, do you wanna just do it during lunch? We'll grab a bite and come back?
Fine, I mean, those guys are coming back, so
Okay.
it's, I mean, if people are hungry, I'll- I mean, I'm trying to, yeah, I wanna run mine, actually, I figured that I might as well do the best demo I can, which is out in the corridor, and
Yeah,
actually
yeah.
make the thing move.
Okay.
If you are taking it out, we'll go with it.
Okay, excellent.
But yeah, we'll have more time later.
Yeah, let's grab something and come back. That way there's no time pressure.
I'll be here if we got.
Yeah, how many people we got online?
Our total head count at peak was 18 total, so.
We got
Yeah.
they may or not, they may or may not be here when we get back.
Yeah, here, we'll, some of us will grab a quick bite and head back.
Chinese place,
Stop the recording. Might figure out how to start it.